Hello everyone. Let us today let us try to understand the Fourier analysis. What exactly this Fourier analysis deals with for signals. Briefly, let us try to understand what are the different analysis we have: Fourier transform and Fourier series. What exactly the Fourier transform is, and what is exactly mean by Fourier series. And now a time domain signal can be converted from time domain to frequency domain. Similarly, how a periodic signal can be expressed with the help of linear combinations of orthogonal functions with the help of Fourier series. So let us try to understand briefly this Fourier transform and Fourier series in this particular session. So Fourier analysis. Fourier analysis. When I say Fourier analysis, Fourier is the name of great French mathematician who proposed this analysis. Because of which this analysis is named after him. So Fourier was a great French mathematician who proposed this analysis. And generally, this Fourier analysis we can understand in two ways. One is Fourier transform. This analysis can be two types: Fourier transform, and second is Fourier series. Now, when I say Fourier transform and Fourier series, we need to understand the very specific difference between the Fourier transform and Fourier series. So, when I say Fourier transform, the fundamental definition of the Fourier transform, which is used to convert a time domain signal to frequency domain signal, and it is applicable for periodic and non-periodic signals. Periodic and non-periodic signals. When I say Fourier series, it is periodic and non-periodic. So for periodic and non-periodic signals, Fourier transform can be applied. So when I say Fourier series, it is applicable for only periodic signals. We'll try to understand why it is, what is mean by applicable for only periodic signals and what is mean by applicable for periodic and non-periodic signals. Generally, if I say the definition of Fourier transform, when I say Fourier transform, I told you this Fourier transform converts a time domain signals. When I say Fourier transform, this converts time domain signal x of t to x of f, and this is a time domain signal and this is a frequency domain signal. So after the application of Fourier transform, a time domain signal is converted into frequency domain signal. Example, if I take x of t versus t is a signal, this is my signal, time domain signal. After the application of this Fourier transform, just I am trying to give you the example, and if it is like this, 0, so minus omega to plus omega, and this is f. So the transformations, this is an application of Fourier transform. X of t versus t became x of f versus f. That means a time domain signal is converted into frequency domain signal. This is not exactly the Fourier transform for this signal. Just for understanding, I have taken this x of f versus x of t versus t becomes x of f versus f. So Fourier transform converts a time domain signal to frequency domain signal. Similarly, when I say it is applicable for periodic or non-periodic signal, in the sense a periodic time domain signal can be converted from time domain to frequency domain. Similarly, a non-periodic signal also can be converted from time domain to frequency domain with the help of Fourier transform. So conclusion is, periodic, non-periodic time domain signals can be converted from time domain to frequency domain with the help of Fourier transform. That is the meaning of applicability of Fourier transform for periodic and non-periodic signals. Coming to the Fourier series, this Fourier series is used to represent the periodic signals. It is applicable only, say it's a periodic signal. When I say xp of t, here we are saying x of t. It can be periodic or non-periodic signal. But when I say periodic, applicable only for periodic signal. And what exactly mean by the Fourier series actually? What exactly mean by the Fourier series? There are periodic signals which are non-sinusoidal signals. There are signals which are periodic but they are non-sinusoidal. What we do is we try to represent them. We try to represent them in sinusoidal form with the help of the Fourier series. So any periodic signal, any non-sinusoidal periodic signal can be expressed as a linear combination of sinusoidal signals with the help of Fourier series. And you can ask me what is the reason why we are trying to represent a non-sinusoidal periodic signal in terms of sinusoidal signals. Can you think about it? What is the reason? Since both are periodic, but why we are trying to represent a non-sinusoidal periodic signal in terms of a linear combination of sinusoidal signals? Can you think about it? The basic reason is analysis any non-sinusoidal signal in terms of sinusoidal signals. When I say sinusoidal signal, you know, like x of t is equal to a cos and if for some periodic signals it's not easy to calculate the amplitude and even frequency and even in the phase. We try to assume the signal, whatever the signal we try to transmit from transmitter to receiver is a sinusoidal signal. Because of that, we try to represent non-sinusoidal signal with the help of Fourier series. So it will not convert to time domain to frequency domain. It only represents non-sinusoidal periodic signal as a linear combination of sinusoidal signals. That is the function of Fourier series. Now maybe let us try to focus what exactly the Fourier transform, in this particular session in detail. So when I say Fourier transform, I told you this Fourier transform converts a time domain signal to frequency domain signal. Time domain signal to frequency domain. And where this x of f can be considered as t varies from minus infinite to plus infinite, x of t e power minus j omega t into dt. This is the fundamental definition of the Fourier transform. Where this omega is equal to 2 pi f. Omega is nothing but angular frequency. Units for angular frequency is radians per second, and whereas this is a natural frequency. The units for this is hertz. Natural frequency, units for this is hertz. And this x of f also can be represented as integration minus infinite to plus infinite x of t e power minus j omega is equal to, if I substitute 2 pi f, j 2 pi f t into dt. This is also another way of expressing this particular frequency the Fourier transform definition. Fourier transform definition. So similar way, we if at all if I have a frequency domain signal, we can get back the time domain signal with the help of Fourier transform. So it's like x of f is nothing but a Fourier transform of x of t, Fourier transform of x of t. So similarly, x of t is nothing but inverse Fourier transform IFT of inverse Fourier transform of x of f. So either of the ways we can use to get x of f from x of t, we apply Fourier transform in x of t frequency domain. So now this is frequency domain and this is time domain. So we are trying to convert a time domain signal to frequency domain signal with the help of Fourier transform. Now even we can say where this omega is equal to 2 pi f, I can represent the inverse Fourier transform definition x of t is equal to integration f varies from minus infinite to plus infinite x of f e power j omega t into df. This also makes sense if it is inverse Fourier transform definition. If x of f is given, from that how do we determine the x of t inverse? There are multiple ways we can write this particular definition, or we can also say x of t can be written as integration minus infinite to plus infinite x of f, where this e power j 2 pi f t into df. This is another way of inverse Fourier transform definition. This is in terms of angular frequency and this is in terms of natural frequency. Even we can express this particular inverse Fourier transform definition in angular frequency. As I said, omega is equal to 2 pi f. When I say omega is equal to 2 pi f, if I differentiate with respect to frequency omega, this will becomes 2 pi into df. So this df can be written as 1 by 2 pi into d omega. So if at all if I want to express the inverse Fourier transform definition, it looks like this: integration minus infinite to plus infinite x of omega e power j omega t into d omega. So when I say this x of f is replaced with x of omega e power j omega t, this df can be replaced by 1 by 2 pi into d. So it will becomes 1 by 2 pi. This is the another way of expressing the inverse Fourier transform definition. So, but most of the situations in the communications, we use this Fourier transform definition to determine the Fourier transform for various signals. X of f is equal to t varies from minus infinite to plus infinite x of t e power minus j 2 pi f t into dt. This is the definition. This is the fundamental Fourier transform used to determine the Fourier transform for different signals. Now let us try to understand how this definition will help us to determine the Fourier transform for various signals. So let us start with a simple question: determine the Fourier transform. Determine the Fourier transform of a rectangular signal. X of t. This is the question. And let us understand how Fourier transform will be determined with the help of this particular fundamental definition. And before determining this Fourier transform, we know rectangular signal x of t is a signal a RECT t by t. This is 0 otherwise. This is when minus t by 2 less than or equal to t less than or equal to t by t, and this is otherwise. How the signal can be represented? Rectangular signal can be represented like this: minus t by 2, 0 plus t by t, and this is t, and this is a. And you know this pulse width is t. Now we are trying to determine for this particular signal. This is the Fourier transform for this particular signal. Now x of t is a rectangular signal. We are interested to calculate this x of f from this fundamental definition. can you think of determining the Fourier transform for this? So when I say Fourier transform definition, the solution x of f, we know x of f is given as integration minus infinite to plus infinite x of t e power minus j 2 pi f t into dt. This is the fundamental definition of Fourier transform. Just think about the limits for a while, whether the limits can be taken from minus infinite to plus infinite even for the rectangular signal, or what could be the limits for this. Right, just cross check. Since it's a general definition of Fourier transform, if x of t lies between minus infinite to plus infinite, it is valid. But in our case, rectangular signal lies between only minus t by 2 to plus t by t. So no need to take the limits from minus infinite to plus infinite. We can take the limits from minus t by 2 to plus t by 2. And in between these two limits, what is the signal actually? Minus t by 2 to plus t by t, the rectangular signal is nothing but a. So rather than taking it as x of t, I am taking it as a, and e power minus j 2 pi f t into dt. This is the way how the signal can be determined, how the Fourier transform can be evaluated with the help of fundamental definition. Now a is a constant. Now I can take it as a is outside, integration minus t by 2 plus t by 2 e power minus j 2 pi f t into dt, and this can be elaborated as a integration of e power minus x becomes e power minus j 2 pi f t divided by minus j 2 pi f, limits from minus t by 2 to plus t by 2, minus t by 2 to plus t by 2. Now if I substitute the upper limit here, this becomes, if I substitute the upper limit, it will becomes a into e power minus j 2 pi f t by 2 minus e power minus j 2 pi f minus t by 2 divided by minus j 2 pi f t, minus j 2 pi f t, minus j 2 pi f t t. So now this 2 will be cancelled, and this 2 will be cancelled, and you will get it as x of f a if I multiply with this minus into minus will becomes plus. So this minus and minus will becomes plus. So we can write it as e power, this term I am writing, this term will be negative. So j 2 pi f, j phi f t, j 2 phi f t minus e power minus j pi f t. j 2 pi f t, j f t, j 2 pi f t, j pi f t divided by, we can write it as j 2 pi f, we already multiplied with minus. So this can be also written as a, we can write it as a by pi f, just for convenience, e power j pi f t minus e power minus j pi f t divided by 2j, divided by 2j. You know, from Euler identities, cos theta can be written as e power j theta minus e power minus j theta divided by 2. Similarly, sin theta can be written as e power j theta minus e power minus j theta divided by 2j. So now I am trying to convert this particular expression into this particular format, e power j theta, because I have 2j pi f here, that's the reason I have taken pi f is at that side, so 2j I have written. A by pi f e power j theta, in the place of theta we have phi f t, j pi f t. This can be approximated exactly as this can be minimized as a into a by pi f into sine theta in the place phi ft will have sine phi ft. So now this can be also a sine pi, just say ft, and here say it as pi ft. We have phi, just I am trying to multiply and dividing with the t. So in order to convert this into this particular format, because now in this case a sine pi lambda, in the place of lambda we have ft pi lambda. So this can be minimized as at sine pi lambda divided by pi lambda can be the sinc lambda, sinc lambda in the place of sinc ft we have. So this is the Fourier transform for the rectangular signal. That means when I say a rect t by t, the Fourier transform is at sinc ft is the Fourier transform. So if you want to see the graphical representation for this particular signal, we can also mention this is x of t, amplitude is a, minus t by 2, 0 plus t by 2, and this is t, and corresponding the sinc function, the corresponding function for this is I'll say x of f, and this is f, and you know sinc function looks like at sinc. This is f, at and so it keep on decreases and it becomes 0 at origin. This is the way how a rectangular this is the way how a Fourier transform for a rectangular signal can be determined, and this also will be considered as the spectrum, the sinc function. This is the spectrum for this rectangular signal, and we are trying to convert a time domain signal to frequency domain signal. So at sinc ft is the Fourier transform for this particular rectangular signal. This is a mathematical representation. This is the graphical representation. So simply I'll try to add one more example here. Suppose if I say this is a rectangular signal 2 and minus 1, 0 plus 1, and this is t, and if I say this is an x of t, what is the Fourier transform for this? Like if we say at sinc ft is the Fourier transform, at sinc ft is the Fourier transform for this. So simply we can write it as this is the Fourier transform. This is the Fourier transform for the rectangular signal. So this way also we can try to determine. This is the way how Fourier transform can be determined for non-periodic signal. This is non-periodic signal. Just I explained same process can be also used to determine the Fourier transform for even periodic signals. Maybe in the next video I'll try to focus on that, and also explain you what exactly how non-sinusoidal periodic can be expressed in terms of sine. Thank you.